All right. What are your group questions or group assignment things that would do like do living organisms disobey the second law of thermodynamics? And I was just curious, like, and again, Christian got asked like what answer do you know? But I told you guys I just kind of hear what you thought. So did anybody respond to that question? What do you guys think?
Yeah, I responded and I think not all of the organisms obey all of the laws.
Okay. Okay. Does anyone else have anything to check?
Even though the order is increased, like because the living almost individual can also break down other complex molecules. They actually the net along the friendliness
Okay, so we consume, right? And when we consume, like if we eat, a plant or something, that's some really highly organized carbon atoms, right? And how do we get that body? How do they leave our body? How's that carbon leave our body? Yeah, we exhale CO2, right? We exhale a gas. So a lot of our fuel we take in as solid, we exhale gas. So we are part of our surroundings, right? So we have exchanges going on with our surroundings. So even though we're highly organized, we are also taking things out and putting things out into our surroundings and causing a lot of disorder. Okay, I just wanted to bring that up. Okay. We started talking about, I said we're going to start talking about reduction potentials and redox chemistry. And so, a lot of times, real quick, before, so we talked a lot about transfers of energy. That's what we talked about on Wednesday. I purposely go through that stuff quickly because I don't want us to get stuck in there. I want us to get into the full metabolism reactions we get to look at for this class. Okay. And so, but we got to look at the transfer of electrons because, like I said, it's going to play a very important part in all the reactions we look at is redox. Okay. Because electrons will spontaneously flow, okay, to molecules that have higher reduction potentials. Okay, that's something you guys have learned in Chem, okay, probably in OChem too. Okay, so we can use the spontaneous flow of electrons, right, to accomplish work. This is another source of energy, the spontaneous flow of electrons. Okay, so if you have two chemical species that differ, let me put up if you have two chemical species that differ in their reduction potentials, okay, you'll get a spontaneous flow of electrons, okay? And so how much force, how much energy you're going to have is going to be proportional to the difference in the electron affinity between those two species. Okay, so we call that the electromotive force. And when we start talking about the electron chain reaction, you'll see. Okay. So in our biological systems, glucose is a great source of electrons. Okay, glucose is a source of electrons. Okay, and so as we talk about metabolism, electrons are going to flow spontaneously through different electron carriers, eventually to oxygen. We said oxygen is our ultimate electron acceptor. We see it's the highest on this reduction potential table. Okay, it has the highest reduction potential. Okay, so. And you guys are maybe familiar with this from a previous class where, you have protons that are pumped to create a gradient, okay? You learned about like the synthesis of ATP, and we'll make a pH gradient, okay? And so, that is all involved in this spontaneous flow of electrons, okay? And like we said, in this reduction potential table, these are all half reactions. Okay, this is only telling you half the story, one of these reactions. Okay, so redox reactions must occur. For a reduction, these are all written as reductions, you have to have oxidation. Okay. Okay, now. Sometimes I feel like it can be hard to see a redox reaction in biological systems. Like in inorganic systems, it's sometimes easier. For instance, if we had like iron 2+ reacting with copper 2+, and we get iron 3+ and copper plus. Right, we might have done this somewhere in Gen Chem. Can you tell which one got oxidized and which one got reduced? Right, if iron 2+ goes to iron 3+, did it gain or lose an electron? It lost an electron. Remember the charge. So it lost an electron. Okay, therefore we say that it got oxidized. Okay. Okay. Now the copper went from 2+ to just plus 1+. So what happened to that guy? What happened to copper? It gains an electron, right? Because this is, remember, electrons are negatively charged, right? And so this is telling you like your proton count, right? This is telling you, okay, I have 2 more protons than I have electrons, so I have a charge of 2+. Okay. Now, if I gain an electron, now I only have 1 more proton, so that's why I have a positive charge. You guys okay with that? Okay, so we gain an electron here. Okay, and when we gain an electron, we call that reduction. I have an ADN class, and then I'm put the table down, and I got the desk in front of it. Good. Okay, I just want to make sure you guys can see. Okay. Okay, so we'll gain electrons, we call it reduction. Okay. So I feel like, you know, from these inorganic examples, you can kind of see what happened to the charge. Did it go up? Did it go down? Okay. Also these terms, right? We say whatever got oxidized, we call that the reducing agent. You remember that? Okay, this is a reducing agent. So in this case, our iron 2+ is a reducing agent. Okay. Whatever gains electrons, it gets reduced. It is considered an oxidizing agent. Or like the oxidant and the reductant. Okay. Okay. You guys have probably seen that before. But if we have something that this is an inorganic example. If we have something like pyruvate, okay, pyruvate plus NADH goes to lactate. Okay, so we have pyruvate going to lactate. And this is a reaction we'll see later. Okay. Can you tell from looking at that, what got reduced and what got oxidized? Dr. Fukuda would believe you all can tell. Right now, you guys all know which one got oxidized and which one got reduced. Okay? But to me, it's a little bit harder to tell. I mean, here, like I said, it's in the charges, I feel like this makes it more obvious in this type of scenario. But in this organic example, right, it's a little bit harder to tell. Okay, well, what do you guys notice? What do you notice about the reaction?
Hydrogens,
The hydrogens, what do you notice about hydrogens?
they moved.
They moved, where'd they go?
NADH lost one,
Okay,
in NAD plus, and
Oh.
then the carbonyl CO became an alcohol.
Oh.
OH.
Oh, okay. Okay, some interesting observations there. Looking at the molecules, so now does it clear which one got oxidized and which one got reduced? Yeah, well, okay, good, yeah, so we look at those things, okay? And there's a couple ways to think about oxidation and reduction, okay? One you probably learned, loss of electrons is oxidation, okay? Like, again, you go Leo the lion says GER or oil rig, whatever, okay? So loss of electrons, oxidation, okay? Another way I like to think about it is loss of my bonds to oxygen. Let's look. Loss of hydrogen, okay, is also oxidation. Okay, that's one way. To me, that's sometimes I have, there's three ways I like to think about these in terms of electrons, hydrogens, and oxygens, okay? And they help me in organic examples, okay? So NADH lost hydrogen. That's an example of oxidation. Okay. Now let's look at what happened to the pyruvate. Okay, as Jasmine told us, right? It went from a carbonyl, which has 2 bonds to oxygen, to an alcohol, which only has 1. Okay, if you lose bonds to oxygen, that typically shows you a reduction. Okay. So here, the pyruvate got reduced to lactate. Okay, it lost some bonds to oxygen. Think about it if it went the other way, right? You go this way, right? If you gain a bond to oxygen, that's a oxidation, okay? So that word oxygen. You lose that bond to oxygen, it's a reduction. It gained hydrogen. It gained hydrogen, which is also gives you a clue that it's a reduction. Okay. So a lot of times in these examples, I might think about my bonds to oxygen or my loss or gain of hydrogen to recognize a redox reaction. Okay. Whenever oxidation goes with dehydrogenation, you guys learned that in organic chemistry, dehydrogenation, the removal of hydrogen. A lot of times you looked at like a long chain fatty acid, a bunch of carbons, maybe like a zigzag line. And then you went from a single bond to a double bond in there. That's a dehydrogenation, okay? And so the enzyme that carries this out, and I'll remind you guys of this later too, are dehydrogenases, okay? So dehydrogenases, whenever you see that enzyme, then you know redox is occurring. Okay, so that's another clue to be able to identify redox reactions. Dehydrogenase, redox. Okay, removal of hydrogen. Okay. Now again, like we said, whether electrons are going to spontaneous flow or not is going to be dependent on their reduction potentials. Okay. And so remember, electrons flow from the molecule with the lower electron reduction potential to molecules with higher reduction potential. Okay, more positive. Okay. All right. So there's actually so notice that it has an apostrophe and a not, right, with a little degree symbol. So these are all standard transform reduction potentials, okay? And there's a relationship between the actual reduction potential, okay, what's actually happening in the cell, and the the constant that you see here in the table. Okay. So actual is equal the standard plus RP and hence that's log of the electron acceptor. I'm not gonna ask you to like, I think there might be some questions in your homework to ask you to do the math, but like on an assessment or an exam, I will ask you to do it, okay? But I want you, I like to look at equations more for the relationships they describe more than anything. Okay. Okay, so R is our gas constant, T is absolute temperature, N is number of electrons transferred, F is Faraday's constant, okay? And so, let's see. What's interesting is that we can use a standard reduction potential to calculate a free energy change, that delta G, okay, that we were talking about on Wednesday, okay? And that relationship is given to us by delta G negative N. Okay. So our Gibbs free energy is related to the difference in our reduction potentials. Okay. And this can be our standard as well. Okay. So we can calculate, right, the delta G for a reaction, for a redox reaction, using the reduction potentials we have in this table. Okay. Okay. So let's go back to this question. I'll let you guys play with these reduction potentials. So I'd like you guys to pair up with at least one other person, or you can go in a bigger group. And I want you, I'll put the table back up, okay? But you got to list the following in order of increasing tendency to accept electrons, okay? So alpha ketoglutarate, oxaloacetate, oxygen, and NADP+. Okay. In order of increasing tendency to accept electrons. Do you guys rather have this up or the table up? The table, okay. Alpha ketoglutarate, oxaloacetate, O2, and NAD+.
Can you go back to the question real quick? So I can just put it up?
Okay, well, I'll write it down.
Oh, thank you.
Alpha ketoglutarate. So this might be hard to see, but again, it's in the book, it's in the slides. If you guys want to look at it closer, or look up the table of standard reduction potentials.
Increasing, they start to.
Could you one more time? What we're looking for? Yeah, the ability to accept electrons, right? So you want to list them in increasing tendency to accept electrons.
Yes.
And talk to someone, you guys. Don't be shy.
Oh.
What are you guys thinking? That's yeah, that one you just need like organic. That we aged. Yes. And the bottom. I don't. Keep going, keep going. Right there. Yeah.
Good. Just trying to get to right hand.
Okay, okay, yeah.
So.
How you doing? Oh, let's see. Okay. I don't even remember what the answer is. I have to go look at the reduction potential. Maybe I should write them down.
Yeah.
See one, like, for example, an AD plus H plus at the bottom,
Uh-huh.
it's the other way to just make it a positive.
Yeah, you put the sign. But which one are you putting the sign for? Are you putting the sign for?
Well, because like in A, it's like acetoacetate plus NADH, and then on the product side, it's NAD plus.
So where are you looking at?
At the bottom, not the bottom, sorry, where you had created initially. So we went from NADH to NAD plus, whereas that is NAD plus to NADH.
But right here?
Yeah, because it's not on the top, right?
No,
Right,
but we don't see it anywhere else up here, right?
right.
Okay, so yeah. Okay. So I kind of went through the table around, wrote down the reduction potentials next to them as well, just to kind of help. Yes,
I have a question. Are we
Yeah.
doing the first one for O2 or the? There's another one on the chart that has just regular O2, it's not half O2.
for this exercise, it doesn't matter.
Okay.
We can use either one. Yeah. Okay. Because either way, it's higher than the other three. Okay, okay, so what you guys do, increasing tendency to accept electrons, increasing tendency. So that means what has the least tendency to accept electrons? Out of these four. Okay, so that's negative 0.166. Is there anything that is even lower? More like larger and negative? Or like, yes, thank you, yeah, okay, I appreciate that. Okay, so negative 0.38 volts, okay, that's our lowest one, so it's gonna have the least tendency to accept electrons. Okay. Okay, so then what would come next? NADP plus, okay, so I don't know if you want to call it second or, second least. I don't know.
Maybe make that 3, and then this is 4.
You want this to be 4,
Yeah.
and this to be 3, okay, okay, and then what would be next? Oxalic acetate, okay, that can be 2, and then, I'm not gonna put that there. And then, so this makes this 1, right, it has the most, it's the highest tendency. So again, just getting you guys familiar, you guys have done this before, you've seen this in Gen Chem, hopefully, I don't know, I talked to my husband, he's like, oh, I kind of rushed through that, I got it. I'm like, great, you know, but just to remind you guys about reduction potentials, it tells you the molecule's ability to reduce, and reduction is a gain of electrons. So it's telling you the molecule's affinity for electrons, okay? The higher the reduction potential, the higher the tendency to accept electrons, okay? So things lower on this table, lower potential to accept electrons, things higher, have a higher, okay? Remember, these are only half reactions. Okay, so now there's a group assignment in Canvas, okay? That we can do. Let's do it under week 2. Oh, no, I'm sorry, still under week 1. Group assignment reactions proceed based on E. Okay. So we can work on this. And again, it's which of the following reactions would you expect to proceed in the direction shown under standard conditions, assuming the appropriate enzymes are present, however. Okay. So have it here. Okay. Oh, but see it got all messed up, but you guys can see. Little friends. But that's okay. So you're gonna need that table again, but now these are written in full reactions. These are not half reactions anymore, like we were looking at before, okay? So there's a couple different ways that people like to look at these reactions, okay? I'll do the first one with you guys, and then I'll let you do the next one on your own. Okay, so I'm gonna erase this. And your book has one way of doing these, and I have enough. Okay, so and I think you'll see. Okay, so remember we said that delta G, right, is equal to this reaction. There was a purpose for that. Okay, and the delta E, okay, as defined by your book, right? And I mean, as defined, the way we define delta E is the reduction potential of the electron acceptor minus the reduction potential of the electron donor. Okay, donor minus acceptor. Okay. That's actually like, so this is one way you can calculate delta G here. Okay, and figure out, is this reaction going to proceed forward, right? If you end up with a negative delta G, then it's spontaneous in the forward direction, or is it going to go backwards? Okay, if it's a positive delta G. Okay. Now, how I like to do these reactions, like the first one, we have acetoacetate plus NADH plus H plus goes to we'll just beta hydroxybutyrate plus NAD plus. Okay, so here's our reaction for A. Okay, now if we go back to that table. we gotta find these reactions. Okay, so we have acetoacetate going to beta hydroxybutyrate right here. Okay, now notice in the question, acetoacetate's on the left and beta hydroxybutyrate on the right, as it's shown on the table. Okay, so it's written the same way as I see it on the table. So I write it down as negative 0.346. Okay. Now the NADH, okay, the NADH going to NAD plus. Well, there it is. The only thing is it's the opposite of what I see on the table. Do you see that? In the question, I have NADH on the left and NAD plus on the right. On the table, I have NAD plus on the left and NADH on the right. So I need to change the sign. Okay, I need to change the sign. So it's 0.320. Then I can add them up. Okay. And again, this is negative, this is positive, so I end up with negative 0.026. Okay. So I end up with a delta E. That's negative. Okay. If that's negative, I end up with a negative times a negative, and I get a positive delta G because of this relationship. Okay, so do you expect that to proceed in the forward direction as written? Huh? No, it wouldn't be spontaneous because it's a positive delta G. Okay, that's a positive delta G. Now, sometimes this might be confusing because we talk about a spontaneous reaction has a negative delta G, but a spontaneous reaction also has a positive delta E, the difference in reduction potentials. Okay, so it's like the opposite. Okay. So remember, negative delta G's give us spontaneous reactions that proceed in the forward direction. You have questions about that? You guys remember that? All right, I'm gonna let you guys work on it, and then because you guys work on the other three. I'm gonna try and take out these extra symbols. Yeah, question.
I was wondering, would you want us to calculate in like an actual number, because if you get a positive delta, how positive does that make the actual?
For the purposes of our class, you can take positive delta E, gives you a negative delta E. And it's all simplification, so parity is positive. So it wouldn't outweigh anything. So if this is negative, you get negative, you get positive. This is positive, you get positive. Has a negative. You get
Yeah.
So actually,
Okay. How are you doing? How are you doing?
Good. I got the constant.
Okay. Yeah, I feel like it's something that took me to remember, like, I'm like, oh. I know I've done it before. You should go earlier, but, yeah, it's fun about that. How you doing, Mom? Okay.
Oh, no.
Oh, no.
Okay.
Yeah. Wow.
Right.
It's really cool.
First, yeah. Okay.
This is the further thing, it's not a G, and a quick explanation, and so it keeps it negative, and therefore the G comes out. This one was negative.
Yes.
Yeah,
Yes, yeah.
Wrong one.
Yeah, no, I'm just kidding. Yeah, no, that's fine.
Okay, so on D,
Yeah.
malate, lactate, this is only one I can think
Two negatives.
So you don't want that because you have malate on the left and then right in the question at here.
Yeah, we're talking about malate and lactate and then.
What? Oh, you have it too, right? You have it. Oh, yeah, I mean, that's on everything. Yeah, all four of them have it. Yeah, wait till you do the last one, phosphorus, something like that. So you have it too. You just gotta figure out which one should you be describing. You know, what side are they on?
Well, no.
Yes.
And that's all the G's and all spontaneous.
Oh, wait, no,
Yeah, so this, the first one is not spontaneous.
Okay.
And then the second one, it comes out. It is spontaneous. And then when it's self, yeah, exactly. It's not why. I'm glad, it's glad we got that figured out, because I was like, yeah.
Oh, yeah, number.
There's like, it's like, I think about it. And not.
Yeah. That's fine. So you guys remember that you do have
It's a
a
combination.
assignment that's due
No.
today by midnight with notes. So yeah,
I was just trying to make sure.
doing it in class today.
And then it's a different group of data. Yeah, that's. I just wanted to make sure.
Are you ready?
Yes, sorry.
Yeah.
This time out, electronics after like production. But calculating.
Had writing.
Never what.
And then they tried to how we were using it, and then we do have behind the counter and make sure it's for the time speaker. It's fine. You're 100%.
There's a great solution. Like you don't want to like. I mean, I love the way it's done, but yeah, it's something. Exam.
Yeah. I work here over the summer and you have to stop.
Yeah. No, I would argue.
Which one am I at? Yeah. I mean, A to B. Pretty ridiculous. It's literally all in the. Yeah. And I'm like, well, my A. is not
All right, you guys, let's look at this, a lot of you guys are chugging along great. Let's look at this second one together. Okay. So we had pyruvate plus NADH and proton going to lactate NAD plus, okay? So pyruvate and lactate, okay, is here. Pyruvate's on the left there, lactate's on the right. In my table, also pyruvate's on the left, lactate's on the right. We get negative 0.185. Okay. Now I have NADH on the left and NAD plus on the right. But here I have NAD plus on the left and NADH on the right. So it's reversed. Okay. And then you always, one of them has to be flipped because again, these are all written as reductions. Okay. And remember here we have a reduction and an oxidation. Okay, so we got to flip this sign. It is negative 0.320 becomes positive. Okay. So then what do you guys get? What's the difference between these?
I got a positive value.
Yeah. Positive what? 135? Okay. So we get a positive delta E. Okay. And again, like people were asking me different questions. I would give you this relationship on an exam, but I wouldn't ask you to do a calculation with this relationship. It's more to see that, right, when I have a positive delta E, I end up with a negative delta G. Meaning it's a spontaneous reaction that proceeds in the forward direction. Okay, are you okay with that? Okay. I want to point out something else. So this is how I like to do it. It just makes sense to me. But the way your book tells you how to figure out delta E is like this, okay? And that's in the slides. And I've had students in the past that like to do it this way, okay? In order to do it that way, I just want to show you briefly how do I do it? What does that mean? Okay, it means you got to figure out which one's the electron acceptor, okay, and which one's the electron donor. So remember, the electron acceptor, right, is the thing getting reduced. Okay, and the electron donor is the one giving away an electron, it's losing an electron. Okay, so we already actually looked at this, right? But you can see NADH is going to NAD plus. We go back to the idea of how do we find redox, right? It lost hydrogen. And in our definition, a loss of hydrogen is an oxidation. Okay. So NADH is getting oxidized. Therefore, it is the electron donor. So when I go find it here, I don't do anything to the sign if I'm going to do it this way. Okay. So we said, what is it? Negative 0.320. That's the electron donor. And so now we've got to say, okay, so pyruvate going to lactate, that's getting reduced. Okay, so that's the electron acceptor. Okay, negative 0.185. So again, it's acceptor minus the donor. Okay, I'm gonna put that in parentheses just to emphasize. Okay, now notice what happens. Now, obviously, I don't like that because I have to think too much. I'm like, oh my gosh, which ones are getting reduced, which one's getting oxidized, but some people like it this way, okay? So, when I do this math, right, it ends up flipping the sign anyways, which we already did the other way, okay, and you'll get the same answer. Okay, but some people like to think about it that way, and that's okay. So you decide what works for you. Okay. Questions about that? And again, I mean, you're still gonna end up. Okay. Alrighty. Okay, I'm going, so make sure you guys do all 4 of them and then make sure you turn it on Canvas, okay? Yeah, no, you just, everyone's turning in. I won't like, yeah, I'm not gonna look at someone else's. Oh, I was in so-and-so's group and they turned it in 30, so, okay. So we will see, notice in these biological reactions, we're seeing electrons getting transferred. And again, like I said, glucose is like a source of electron in these reactions, okay? And the electrons are going to get transferred from glucose in a series of redox reactions, and they often require a coenzyme. So we said dehydrogenases are going to be the enzymes that carry these out, but often the dehydrogenases need a coenzyme, okay? Something like NAD is a coenzyme, okay? And what it does is it carries electrons. It carries electrons. Let's look at. So you guys have probably, maybe in the past, just maybe in a biology class, just called NAD, okay? But it stands for nicotinamide adenine dinucleotide, okay? Sometimes the coenzyme is NADP. You have seen that, and if that's the case, it has the same structure. It's just that there is a phosphate group. Now we have in this structure we have our nitrogenous base adenine, right, connected to the ribose ring, okay, and with the phosphate backbone. So you guys have seen these in your nucleotide structures, okay. But notice here we have another ribose ring connected to this nicotinamide ring, okay? And that is what makes it possible. It's this ring where the electrons can be either accepted or donated. Okay, this is how it works as a coenzyme in the reduced form. Okay, so we go from NAD plus here to NADH. Okay, you get NAD from niacin. It's a vitamin. Okay, so we get it from you have that from niacin. NAD tends to be diffusible. It's not tightly bound to the proteins they help. Okay, it's not tightly associated. Again, it can undergo this this is reversible. It can accept electrons. It can donate electrons. Okay. So that's going to do with the stereochemistry, depending on how the reduction goes. So that is just the different. Notice that this one, the protons that get added, that's like a OChem thing, right? Is the OChem getting added to the proton getting added to the top of the ring or the bottom of the ring, A side or B side? Okay. So notice that NAD plus accepts hydride ion. Okay, it accepts 2 electrons and it gets reduced to NADH. Okay. Okay. Now we say NAD plus to emphasize the oxidized form. Okay, you see that? That's how we know it's oxidized. NADH is the reduced form. Should get really familiar with that. Get like NAD plus oxidized form, NADH is reduced form. Okay. This doesn't indicate charge. Notice it's actually negatively charged, right? It has these 2 negative charges in the phosphates here. and this one positive charge here. So overall, the molecule actually has a negative charge. This does not indicate charge. That indicates that it is oxidized form. Okay. All right. And like I said, depending on the enzyme, it might have a different cofactor of NADP. Okay, and that just means that there's a phosphate group attached to this ribose ring. So whether it's NAD or NADP. Okay. Questions about NAD? Yeah.
You said that overall it was negative?
It is, it overall has a negative charge, yeah, but we write NAD plus, it can be very confusing, right? But again, that plus just indicates it's a oxidized form. Now, NAD has a really, really cool property, okay? And that property, I mean, it doesn't seem that cool now, but if you're in 441, you might actually have to use this, okay? Is that NAD can be, you can monitor whether it's oxidized or reduced using UV vis. Okay, that's a very, very handy property of NAD. Okay, so the reduced form displays a peak at 340 nanometers. Okay, in blue is your reduced spectrum. Okay, and red is your oxidized spectrum. And notice the reduced form has a peak at 340 and the oxidized doesn't. So you can monitor the activity of an enzyme with UV vis. And I love monitoring things with UV vis. I feel like it's really straightforward. Right there, very accessible. One of the more well-behaved instruments in the lab. Okay. So this is very important in enzymatic assays. Okay, so again, it gives us a way to measure enzyme activity. Okay. Right. Want to say there is also another cofactor we'll see is flavin mononucleotide. Okay. FMN or flavin adenine dinucleotide, FAD. So these are other cofactors that carry electrons for us. Okay. Again, notice we have a similar adenine base attached to a ribose ring. We have those phosphate groups, but now instead of that nicotinamide ring, you have this isoalloxidine ring. Okay, and this again, this is the ring that allows the accept or donation of electrons. Okay. The source of flavin is from riboflavin. Okay. So that fused ring structure can undergo reversible reduction. Now, the interesting thing about FAD and FMN is that they can accept one electron and form the semiquinone molecule, okay? Or they can accept two electrons to become fully reduced, okay? So the way we show the fully reduced is when they have that H2, FADH2 tells you it's fully reduced. FAD means it's oxidized. Okay, the gain of hydrogen, okay, is helping us see that redox chemistry going on. Okay, again, FADH with the dot is that semiquinone, just one electron added. Now, if you've been in our group meetings, okay, a question often comes up when you're talking about a protein or about an enzyme. Is it a flavoenzyme? Is it a flavoenzyme? Okay, I hear that question all the time. So when you're studying enzymes, you're learning about enzymes, you need to understand, is it a flavoenzyme? Okay, does it require FAD to do its job? Okay. Now, flavin cofactors are tightly bound to proteins, as opposed to NAD that were, remember, those ones are diffusible, they can move around. So the flavins tend to have these tightly bound, and if for some reason, if you've done some work and you somehow disconnected them, then the enzyme's not going to work the way you would expect it to. Okay. So some differences. Okay. So again, it can carry one or two electrons, and it's tightly bound to the enzyme that it works with. Okay, so these are the electron carrier, these cofactors that carry electrons for us. Very important. Okay. Questions? Yeah,
So. Tightly bound, does that also mean that it tends to just like. To the protein and stay with the protein?
it can be covalently bound to the active side of the protein, yeah. Other questions? Okay, so as far as that first section, that kind of reviews everything. That's all I have to say. I know there's a lot of other things. I think I need to move that table into my slides out of the Leninger slides, but besides that, there's a lot of things in the Leninger slides that I did not cover, okay? That you're free to look at, but, they're, yeah, there for more information, okay? You guys have a pre-assignment due for, we're gonna start talking about glycolysis, okay? So that's where we're going next, okay? And so you guys have another pre-assignment that's due on Wednesday, okay? So for week 2, you have this class prep, and it's section 25 in your workbook. I'm gonna just double check because some of the sections change. Yeah, section 25, enzymes and glycolysis, okay? So is anyone having trouble getting, I don't know what, okay. Anyone having trouble getting the workbook? Okay, let me know, okay? But that pre-assignment is for Wednesday. So we can start looking. There's also these links to videos, if you guys like to watch videos, the animation of glycolysis. And then a more in-depth look at it. Now we're going to start looking at glycolysis, getting into the reactions, gluconeogenesis and the pentose phosphate pathway. Okay, so when we think big picture, we're thinking like carbohydrates, fats, proteins. Okay, and again, build up and break down. Okay, so glycolysis, right? It has to do with the breakdown of carbohydrates, specifically glucose. Okay. So this is a big overview. Okay. So glycolysis tends to be broken up into 2 phases. The first phase is called the preparatory phase. Okay. The second phase is called the payoff phase. And just big picture, like notice this is our glucose molecule. I always like to think of it as having 6 carbons. That's important. Okay. I like to count carbons a lot in this class. I find it very helpful in understanding what the reactions are doing. Okay. So we take 6 carbons, they get phosphorylated. So when glucose is taken up, you have to think about like we'll look at this, but you eat something, okay, like starchy, it breaks down the starch into glucose molecules. The glucose goes into your blood, increasing your glucose concentrations in your blood, and then your cells uptake the glucose to help reduce the glucose in your blood, okay? So in order for this to carry out, it's got to keep the glucose in the cell. And the way it does that, that very first step is phosphorylated, okay? Notice the phosphate group is represented here in this orange circle with the P. Notice that it remains phosphorylated throughout the whole process, okay? And again, that keeps the molecules in the cell, that phosphorylation, okay? As we go through this process, you'll see it gets phosphorylated. Notice as we move through the steps, it gets, and we're going to go through each step in a lot of detail. Okay, this is just introduction and overview. It gets symmetrical, okay? Because then we're going to split the molecule into 2 3 carbon molecules. Okay, so we go from 6 to 3 carbons. And we end up with 2 pyruvate molecules, 2 3-carbon molecules, okay? Also, along the way, notice some of these enzyme names. So when, throughout these slides, when you guys are looking at them, they're the enzymes that are catalyzing the steps are shown in blue. So you have to think for each step occurring, this molecule is hanging out on the active site of an enzyme, which is a big, huge, right? Well, they vary in size, but right, it's an enzyme made up of amino acids, okay, and it's in the active site. So like the first one is hexokinase, okay, isomerase, fructokinase. These are all the enzymes that carry out each of these steps, okay. The second phase is called the payoff phase, because in the payoff phase, you get the formation of ATP, okay, which we call the currency, right? Notice we had to donate ATP here, okay? We had to donate ATP in the preparatory phase, but we get ATP out, and we get it again here, okay? So we put 2 ATP in the prep phase, but we get 4 ATP out in the payoff phase, okay? We also get NADH, which is seen as like the increase in our currency, okay? Notice those reactions that do that. Look at the name, dehydrogenase. Okay, so we know there's some redox going on there. We can see some electron carriers there. NAD plus, we said is an electron carrier. Okay, so all indicative that there's redox going on here. Okay, so what's interesting is that glycolysis is one of the most studied reactions in metabolism. And the same 10 steps that we use in our body, like yeast use it, okay? And so I want you to think about, like this has been conserved throughout evolution, is these 10 steps of glycolysis, okay? So what do you guys think? What's the significance that the chemistry of the reactions of glycolysis have been completely conserved, and the enzymes of this pathway are similar in amino acid sequence and 3D structure from yeast, spinach, to vertebrates. Okay, all use the same 10 steps, very similar. Okay, well, why don't you guys talk to each other? I'll be quiet for a minute. Let you guys just let that sink in, the significance of that. What do you guys think? Oh, I got it.
Like, that availability of substance abuse and engineer. Like, yes, environments, other words, there. Or like. That. Yeah, so I would say, I know that is very efficient. You know, when to explore, but in.
So it's necessary. At least.
Yeah.
That's what I'm saying. Yeah. I think there's like a flip on hydrogen. They're like.
Okay.
Like my brain
Yeah.
went to like, what if these are them?
Yeah, and even like.
What's the significance of that chemistry?
It's
Yeah,
I mean, when we have found a different way to do it in different like species if there was like a more efficient way to do it.
Right, there was a better way to do it.
So it's like, I feel like we would have evolved a different way to do it if there was a more efficient way.
Yes, and so, I mean, and it also speaks to the importance, right? It's like, yeah, like this is the best way to extract electrons from glucose. Okay? This is the best way to do it, okay? And it's been conserved, like, it's weird to think that this is the way spinach does it too. Right? Isn't that funny? I don't know, I need time to think about that. Okay. And again, I wanna point out that this is, in glycolysis, this is a catabolic pathway, okay? This is a breaking down pathway of glucose, okay? So again, we see that it gets phosphorylated by ATP. ATP is our phosphate donor, okay? And then we see it undergoes an isomerization, okay? So from glucose to fructose, okay? So from a 6-membered ring to a 5-membered ring. We have another phosphate donated from ATP. Okay, so now we got this bisphosphate, 1,6 bisphosphate. And then we have the cleavage of the 6-carbon molecule, okay, to 2 3-carbon molecules. In the payoff phase, only one of these, so you end up with glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. These are the 2 molecules you end up with. Only the glyceraldehyde 3-phosphate proceeds through the next steps. So there's an isomerization that takes place. The dihydroxyacetone phosphate isomerizes to glyceraldehyde 3-phosphate. Okay. So now we're going to get a conversion of this glyceraldehyde 3-phosphate to pyruvate. Okay. In that process of going from glyceraldehyde 3-phosphate to pyruvate at the bottom, we are going to get the formation of electron carriers in the form of NADH. Okay, so this first one. Notice there's phosphate. It gets phosphorylated again, but notice that ATP is not the donor here. Okay, that PI in these just stand for inorganic phosphate. So it's a phosphate group. NAD plus gets reduced to NADH. Okay. Let's see, can you guys see the oxidation in going from glyceraldehyde 3-phosphate to this 1,3-bis-phosphoglycerate? This molecule?
Yeah.
Yeah, do you see this carbonyl, right? It has 2 bonds to oxygen. And then if you go down here, now it has 1, 2, 3 bonds to oxygen. Okay, it got oxidized. NAD plus got reduced. Then we get our ATP formed, and it says 2 because you have to remember for every 1 molecule of glucose in that preparatory phase, we have 2 molecules of the glyceraldehyde 3-phosphate going through this payoff phase, right? We have a 6-carbon molecule, we split it into 2 3-carbon molecules. Each of those molecules can go through this payoff phase. All right. So that's why it says 2 ATP. Go through another isomerization, okay, and then we get another formation of ATP in that last step, and we end up with pyruvate at the end here, okay, at the end of this glycolysis reaction. Now the pyruvate can do a couple things, and we'll talk more about all of these. Again, we'll talk about all this in a lot of detail, but from that 1 glucose molecule, you get 2 pyruvate molecules, and depending on the situation, right, and what kind of organism you are, okay, under aerobic conditions with oxygen present, right, the pyruvate can continue to make acetyl-CoA, and that can feed to the citric acid cycle, okay, but this is, you need oxygen present to proceed through that pathway, okay. Now, if you're yeast, okay, pyruvate, and you're under anaerobic or hypoxic, meaning low oxygen conditions, then that pyruvate undergoes fermentation, right? And that's where you get ethanol and carbon dioxide. Okay, so you guys know like fermenting for wine, for beer, for alcohol, right? That's this process. In us, we can also do fermentation, okay, but we don't produce ethanol. We produce lactate. Okay, and I heard a lot of you guys talk about that when you were talking about what burns more fat, walking or running. A lot of people talk about production of lactic acid. Okay, so that's this. Again, if you're running, you're not as able to take in as much oxygen, and you start getting into these hypoxic conditions or anaerobic conditions, and you start producing lactate. Okay. Okay, so we get to we'll look at all this in a lot more detail. But I'm gonna stop for now. Questions for me? Okay, so we're starting glycolysis. Yay, it's gonna be exciting, okay? Like I said, you guys have your group assignment due on those reduction potentials. And you have, the prep assignment for looking at the different, reactions in glycolysis.
Yeah, you too.
Right? You guys enjoy the rest of your day.
Well, I just want to get started on it because I have to do this.